We've talked about several examples of games, and now we want to do is pick a specific game and begin to analyze it in some detail. The game we're going to look at is called The Prisoner's Dilemma, and it's called that because, in fact, it actually is about prisoners. And if you've ever watched a police drama, you've seen some version of this game played out on television. The story is that the police have arrested two suspects in a crime, and they're certain these two people committed the crime. They just don't have enough evidence to convict them of the crime. The only way they're going to get a conviction is if someone, or perhaps both of them, confess. So what they do is they put the two suspects in separate rooms, and they tell each suspect that if they confess, they get turned free. All they have to do is testify against the other person who's going to go to jail for a long time. And of course, each suspect is also told that if they don't confess and the other one does, then they're the one who goes to jail and the other one goes free. What the police often conveniently forget to tell the suspects is what's going to happen if they both confess or if neither confess. But we're going to need that to actually analyze the game. So we have to have some payoffs for that. If they both confess, they both get sent to jail for a while, but not as long as it would have been the case for the person who didn't confess when one does. And if neither confess, then they both are going to get sent to jail in my example, but not for very long. Perhaps they can be convicted of possession of stolen property, the property that they actually stole. To analyze this game, we're going to have to set up some structure. So the structure we're going to look at is going to be called a two-person game. Each person can choose a strategy of confess, represented by C, or not confess, represented by NC. Player 1 in our game chooses rows in this matrix, and player 2 chooses columns. So, for example, if player 2 chooses to confess and 1 does not confess, then what happens is that because 2 confessed and 1 didn't, 2 gets turned free. So his payoff is 0. 1 who didn't confess when 2 did gets sent to prison. In our matrix here, we have him going to prison for 9 months, and we have a minus sign on that because more time in prison is worse than less time in prison. So let's figure out what these players are going to do. Let's start by analyzing the game from the point of view of player 1. Player 1 should say to himself, if 2 confesses, what should I do? Well, if 2 confesses, we're in the first column. 1 will go to prison for 5 months if he confesses. He'll go to prison for 9 months if he doesn't confess. So, of course, he should confess. Alternatively, he should say, what am I going to do if 2 doesn't confess? Well, if 2 doesn't confess and 1 does, 1 gets turned free. Whereas if 2 doesn't confess and 1 also doesn't confess, 1 goes to prison for 1 month. Being turned loose is better than a month in prison, so 1 should confess. Notice here that what we have is that 1 always chooses to confess no matter what he thinks 2 is going to do. And this game is actually completely symmetric, so it's the same from 2's point of view. 2 is going to choose confess no matter what he thinks player 1 is going to do. And of course, if you think about this, this is why the police like to play this game out, because both suspects are going to confess. It's the right thing to do regardless of what they think the other person's going to do. Now that's a cute story, it's a simple game. What we want to do is take these ideas and apply them more generally to other games. We're going to look mostly at two-player games. We're going to give our players the rather boring names of 1 and 2. And they're each going to have some strategies they can possibly follow. In Prisoner's Dilemma, it was confess and not confess. It might be up and down. There might be more than 2 strategies as well. It could be left, middle, and right. We're always going to represent their payoffs in a simple payoff matrix. To begin our analysis of game theory, we're going to need a little bit of terminology. And in fact, we need 2 definitions, just 2 for now. The first one is what does it mean for a strategy to be a best response? We're going to say that a strategy S for 1 for player 1 is a best response to some strategy S2 for player 2 if S1 makes player 1 as well off as he can be, given that he thinks 2 is going to actually play S2. What we saw in the Prisoner's Dilemma was that for player 1, confess is a best response to not confess, and confess is a best response to confess. Right? That is, we saw that confess was always a best response. And we saw the same thing for player 2. The other terminology we need is what it means for strategy to be a dominant strategy. Strategy is dominant if it's always a best response no matter what you think the other person's going to do. And in Prisoner's Dilemma, there was a dominant strategy. In fact, for each player there's a dominant strategy. It's simply confess. It's always the best response. Okay. That's why in Prisoner's Dilemma, we're pretty confident about the prediction of confess for both players. Now, this was a simple example, but this example illustrates a phenomenon that happens in actually quite a few games, not just in the Prisoner's Dilemma game. For example, it happens in arms races. Think about two nations deciding how to divide their expenditures between money spent on the military and money spent on goods for consumers. Depending on what the payoffs are, it can easily be the case that military expenditures being high is a dominant strategy. You see the same sort of thing in, for example, games where we consider use of performance-enhancing drugs in sports. Depending on what the payoffs are, it can easily be a case here again that using performance-enhancing drugs is a dominant strategy for all the participants in the sport. This also occurs in pricing games. Someone who's introducing a new product into a market where a firm already has a very similar product may find that low pricing is a dominant strategy, even though it might result in relatively low payoffs. You see this as well played out in price wars for airline seats or for hotel rooms, where airlines and hotels often are forced to charge low prices because low pricing is simply a dominant strategy for them. Lots of games have dominant strategies, many others don't, and what we want to do next is figure out what's going to happen in a game when one or both players don't have dominant strategies.